So, this would be the last class of transport phenomena. I hope you have enjoyed this course. The primary objective with which we have started this course is to give you an idea about the different type of transport processes can be tied together by an unified treatment. So, this course is therefore a unified treatment of heat, mass and momentum transfer. In this last class, I will give you an overview which is essentially the summary of the objectives of the course with which we have started and what we have done to fulfill each of those objectives. So, there would be tutorial problems. There are a number of problems which I have solved in the class to clarify your concepts, to clarify your doubts, and if there are anything remaining, anything that you would like me to address once again, please write to me and I will try to make sure that those concepts are explained to your satisfaction. So, what we have done in transport phenomena, let us start with that. But before we do that, let us quickly review what are the requirements of transport phenomena, the textbooks that I have prescribed for the course and so on. So, I first start with this where we said that it is a basic fundamental course in chemical engineering. However, the concepts that we have developed in here would find use in mechanical, biotechnology, nanotechnology and several other areas in which one has to model a process for which the relations or correlations are not known to you. How can you start with the basic physical principles governing heat, mass and momentum transfer and arrive at a fundamental governing equation? You also have to understand the process so that you will be able to suggest what are the possible physical boundary conditions that your system must obey. For example, it could be the no slip condition, it could be the adiabatic surface in terms of heat and mass transfer and so many, it is a very fast reaction, a slow reaction, so many different types of examples of boundary conditions that we have discussed in this course. So, even though it is a course of chemical engineering, I think it would be equally applicable to anyone who is trying to find out the science behind observations that you see in the laboratory, that you see around you. So, whenever you observe a new phenomena, as an engineer, as a scientist, you would like to model that. So, in order to model that, the fundamental forces which are at play in that process need to be examined carefully. Their interrelations would have to be established through the use of appropriate modeling. So, this course not only teaches you the fundamentals of heat, mass, momentum that you have already studied, this is a training for you to see how a process can be modeled. So, we started our transport phenomena with the basic book, which the book that I have referred to many times in this course is that by Bird, Stewart and Lightfoot, which was published maybe about 50 years back, but it is very relevant even today, and it has made a paradigm change in how chemical engineering is taught throughout the world. So, the unified treatment that Bird, Stewart and Lightfoot proposed in 1960s is still a valid concept. It is a concept which students everywhere still try to understand. So, I wanted to give you that flavor in this course. So, the first book that I have prescribed for this is Transport Phenomena by Bird, Stewart and Lightfoot, and the second book which you probably have studied before is Fluid Mechanics by Fox and MacDonald. And the third, so this fluid mechanics, this book by Fox and MacDonald I have extensively used for boundary layers and related concepts. And the third one is Introduction to Heat and Mass Transfer by Incropera and DeWitt, which I have used for our treatment of the similarity, the equations and so on. So, if I look at formally the course plans, and let us try to see what we could achieve in this course. So, the first we started with the fundamental concepts of momentum transfer. I started with shell balance, and the shell balance is a unique and handy way to treat simple problems. So, you devise so you think of a shell and you create that, you make the momentum balance, which are the forces acting on it. And we have identified the forces to be of two different types. One is due to the surface forces, and of surface forces we took the examples of there is a pressure difference which causes the flow, and there is a shear interaction between layers of fluid which are slipping past each other. So, shear is some sort of a restoring force, shear which opposes the flow. So, pressure and shear are the two forces which we have analyzed under the category of surface forces. And there would also obviously be body forces, and the most common body force is gravity. So, your shell balance essentially tells you that the rate of momentum into a control volume, and the momentum in can be by two mechanisms. One is by convection and the other is by conduction or diffusive momentum transport. So, when I talk about convection, it is due to the actual flow into the control volume. So, we now know how to express the convective transport of momentum inside the shell, and we also know that the shear stress is going to be felt by a surface which is parallel to the direction of flow. So, the area through which mass and momentum comes in and the area on which the shear forces would act are different. So, we have done that in our shell momentum balance. So, from a difference equation we have obtained a differential equation that governs the process, and then we solve the differential equation with the help of appropriate boundary conditions, namely no slip and no shear. So, that is what we have covered in the first 2 weeks to formulate and to solve the momentum transfer in laminar flow. But we have realized at some point that it is becoming increasingly difficult to do a shell momentum balance and to arrive at solutions. This is particularly true when we talk about when there are multidimensional effects, when we have transient flow present in transient condition present in the flow. So, the need for a generalized treatment of momentum transfer in the form of a general equation that takes care of all these transport through the momentum transport by two means: the pressure force, the surface force, the time dependent, the transient nature of the flow. All those can be put together in the form of a general equation which we have derived in the class, and which is Navier-Stokes equation. And we have Navier-Stokes equation in rectangular coordinates, cylindrical coordinates and in spherical coordinates. So, we need to choose the right component of Navier-Stokes equation from those available in your text. You do not have to remember Navier-Stokes equation, but you should know which component to choose. So, for a Cartesian coordinate, find out which is the principal direction of flow and choose that as to be the governing equation that needs to be used for subsequent solution of the velocity profile. So, we know what is Navier-Stokes equation, how to use Navier-Stokes equation, the same boundary conditions would apply. So, comparing the shell momentum balance and Navier-Stokes equation, you could quickly appreciate the utility of Navier-Stokes equation in the formulation of the problem and the governing equation. So, that is what we covered significantly. Then came the boundary layer concepts, the boundary layer thicknesses and so on. So, what we have done in those two or 3 weeks is introduce the concept of boundary layers, that there exists a thin layer very close to the solid surface, which is responsible for all transport phenomena that you can think of, be it mass transfer, momentum transfer or heat transfer. Everything is confined in that thin layer close to the solid surface. Inside the boundary layer, the flow is two dimensional. Outside the boundary layer, the flow can be treated as inviscid flow. So, boundary layer is the missing link between experiments and theory that existed in the early 19th century. So, the concept of boundary layer is further enhanced by the definitions of what is the boundary layer thickness, and we understood that evaluating the boundary layer thickness is a difficult proposition. So, instead of boundary layer thickness, we have introduced the concept of integral thicknesses, namely the displacement thickness and the momentum thickness, which allowed the interpretation of the data in a way that would minimize the experimental errors. So, the way this boundary layer has been treated, especially for the simplest possible case of flow over laminar flow over a flat plate, that is, we use the Blasius formulation to obtain a dimensionless higher order ordinary differential equation using the concept of a boundary layer approximation and using the solution methodology of combination of variables. So, we defined a similarity parameter, transformed the partial differential equation to an ordinary differential equation, and numerically solved the equation to obtain a table which contains the values of eta, which is the dimensionless distance, and we have evaluated what are the dimensionless stream functions, which are f, the f prime, f double prime, and so on. And we already know what is the relation of velocity with f, f prime, and so on. So, with the Blasius exact solution approach and with the help of numerical solution, we obtained closed form solutions of delta, compact expressions of delta, the thickness of boundary layer as a function of Reynolds number. And we have also obtained what is the friction coefficient Cf, the friction coefficient, which is essentially the wall shear stress divided by half rho E square. What would be the expression of that if we go for analytical solution of boundary layer flow over a flat plate? While doing that, we understood that it is not sufficient, it is not enough, because even the simplest possible case resulted in a partial differential equation. Analytical solution was not possible, numerical solution had to be used. So, how are we going to treat cases in which the area over which the boundary layer forms is curved? What happens if instead of laminar flow we have turbulent flow? So, this has established the need for a more general, approximate but more general method. So, we then went ahead and we derived the momentum integral equation. As the name suggests, it is an integral equation, and the advantage of that, it is not restricted to laminar flow or turbulent flow. The only thing you need in order to solve momentum integral equation, which by the way is an ordinary differential equation, is an assumed velocity profile inside the boundary layer that needs to satisfy the conditions at the solid liquid interface and at the edge of the boundary layer. So, with an assumed velocity profile, we then proceeded to benchmark our results against the one which is already available. So, we already know what would be the boundary layer thickness variation with Reynolds number in laminar flow over a flat plate. So, we used momentum integral equation to obtain the same relation, to obtain the expression for Cf, and we saw that the variation was very small. Even with the approximations used in momentum integral equation, it was very successful in obtaining an expression of delta or Cf that is almost the same as that obtained from a very lengthy and complicated procedure of solving partial differential equations in differential analysis of fluid motion. So, an integral motion, integral analysis therefore was always preferred, because it gave us a handy way, a convenient way to solve for situations not only laminar. We then went for turbulent boundary layer, and in the turbulent, not only in the turbulent boundary layer, where we have used the some of the other approximations, for example, the expression of the friction factor in turbulent flow and so on. We then obtained what would be the growth of the boundary layer, what is going to be the friction factor for mixed flow cases, because most likely the boundary layer is going to start as laminar, then after it reaches a certain distance, after it covers a certain distance, the value of Reynolds number to be equal to 5 into 10 to the power 5, which is only a convention that from that point onwards the flow inside the boundary layer is going to be turbulent, and we know that turbulent boundary layer grows faster than the laminar boundary layer. So for those cases where the boundary layer is initially laminar and then it has become turbulent, that is mixed boundary layer cases, we obtained what would be the functions, what would be the expressions for Cf and so on. So that is what we have covered in momentum integral equation in turbulent boundary layers, and we have also covered the concept of drag, the drag forces, and we have been exposed to the beautiful examples of how a cricket ball would swing in air. So I think that was quite interesting to show that there would be difference in pressure on an object based on whether you have laminar flow on one side and turbulent flow on the other side. Such pressure difference would probably ensure that the moving object will try to move away from its straight line path. So we have had a good example of swinging of cricket ball into to finish with our understanding of what is drag and how it works. From that point onwards, we then shifted gears to heat transfer, and the same way we have done a shell heat balance method to end with appropriate boundary conditions. We solved some of the examples of heat transfer in laminar flow, heat transfer in solids, heat transfer in solids where the temperature could also be a function of time, and in there where we have the temperature varies with xyz and temperature can also vary with time, we have introduced the concept of lumped capacitance formulation, which tells you that the entire process of modeling heat transfer, modeling transient heat transfer, can be simplified significantly if it is assumed that inside the solid object the temperature does not vary with spatial positions. So T is not a function of x, y, z, T, the temperature, is only a function of time. So if we do that lumped capacitance, and we have discussed when this lumped capacitance model approach would be valid, then the problem of transient heat conduction, and for special cases where one end of the solid which was initially at uniform temperature is suddenly changed to another temperature. So if one end of a solid with uniform temperature is suddenly exposed to a different temperature, how would the temperature inside the solid will change as a function of position and as a function of time, and we saw the error function solution in it. This error function keeps on coming back in many of the transport phenomena problems. For example, when you have a solid plate and a pool of liquid above it, and if you suddenly set the solid plate in motion, then the velocity in here in this pool of liquid above the moving plate, above the plate which is suddenly set in motion, also will change in error function, and we have solved that problem in class. So going back quickly once again, the first few weeks up to Navier-Stokes equation, we have used extensively Bird-Stewart-Lightfoot, the textbook of Bird-Stewart-Lightfoot. The boundary layer concepts, the momentum integral equation, this was from the book of Fluid Mechanics by Fox and MacDonald, as well as in Bird-Stewart-Lightfoot. So, the first 2-3 weeks it was Bird-Stewart-Lightfoot only, then we have Navier-Stokes equation. This Navier-Stokes equation was from Bird-Stewart-Lightfoot as well as from Fox and MacDonald, but the boundary layer concept, the momentum integral equation, that was entirely from Fox and MacDonald. Then we solved the heat transfer using the same approach of shell heat balance. We saw the need for having a general solution, so we went ahead and obtained the energy equation, the transient conduction that I have just described, the analytical solutions, for example, an error function solution and other methods. So, this is mostly from Bird-Stewart-Lightfoot, and the other book on heat and mass transfer, which is by Incropera and Dewitt. So, the Incropera and Dewitt, that book we have used for definitely for transient conduction, but for formulation of heat transfer and energy equation we have covered from Bird-Stewart-Lightfoot. So, week 6, 7 and 8 are from two books, what is Bird-Stewart-Lightfoot and Incropera and Dewitt. With this behind us, from week 9 and week 10 we have worked on mass transfer. So, the same way we have done for heat transfer and momentum transfer, we started with shell mass balance. We wrote the equation, the species equation, which is essentially an extension of the equation of continuity, and there we saw that the generation of a species or the depletion of a species can take place through reactions with another reactant which is present. So, the source or sink term in the form of equation, in the form of reaction, will appear in the species balance equation. But we also understood that as long as this reaction is homogeneous reaction, that is, this reaction is taking place everywhere in the reaction medium, it would appear as a separate generation term in the species balance equation. If it is a heterogeneous reaction, a catalytic reaction which takes place only on the catalyst surface at a specific location, then it would not appear in the governing equation. The presence of a catalytic reaction, a reaction which takes place on a surface, will be accounted for by the boundary conditions. So, the major point here is that the species balance equation is similar in concept to the one, the heat balance, the momentum balance that we have derived before, but the generation term here, if it is a homogeneous reaction, it is going to come in the governing equation. If it is a heterogeneous reaction, it is going to come in the form of boundary conditions on the surface. And these heterogeneous reaction, the implication of having a very fast reaction or a slow reaction, that we have gone through two examples where a fast reaction is taking place, making the reactant concentration on the surface to be equal to 0, and a slow reaction which would ensure that some reactant will exist on the surface, and at steady state the diffusion of reactants towards the catalyst surface must equal to the reaction rate. So, requirement of steady state demands that these two rates, the diffusion rate and the reaction rate on the catalyst surface, must be equal. So, we have solved a number of interesting problems on mass transfer in those weeks, and I have extensively used Bird-Stewart and Lightfoot, both for the shell mass balance, for the development of the species balance equations and so on, but I have also taken examples from the book of heat and mass transfer by Incropera and DeWitt to solve some of the problems which are even more interesting. So those weeks, the week 9 and 10 for mass transfer is mostly from Bird, Stewart and Lightfoot. And in the last 2 weeks, the past 2 weeks, we are after we have studied momentum transfer, heat transfer, mass transfer, Navier-Stokes equation, energy equation, species balance equation, we saw that what binds them together is the location where all of this is taking place, the concept of boundary layer. So we wanted to see if the equations of heat transfer, mass transfer and momentum transfer inside the boundary layer can be explored, can be analyzed, can be looked into in more details to obtain the similarity. So what we have done is we wrote the equations and we non-dimensionalized them. The moment we non-dimensionalized, some of the similarity parameters automatically came out of those equations. So when we non-dimensionalize the Navier-Stokes equation inside the boundary layer with the boundary layer approximations, Reynolds number came out of that. When we have done the same with energy equation inside the boundary layer, we saw its Reynolds number and Prandtl number which were the similarity parameters. And for the case of mass transfer, it's Reynolds number and Schmidt number. So when we place all these three equations side by side, we start to see a similarity. The similarity would be even more prominent if I could make the Prandtl number and Schmidt number, the value of the Prandtl number and Schmidt number equal to 1, which is a very strong assumption, which is a very I mean, this assumption can obviously be questioned, but let us assume that the Prandtl number and Schmidt number, they are equal to 1, and let us assume that the effect of dp dx, which is there in the governing equation for momentum transfer, is 0. So if dp dx is 0, Prandtl number and Schmidt number are equal to 1, then all these three equations will be identical. One is in terms of velocity, the other is in terms of temperature, and the third one is in terms of concentration. These three equations are identical, and when you see the boundary conditions on the surface and at the free stream, when you look at the boundary conditions with all these assumptions, dp dx 0, Prandtl, Schmidt equal to 1, the boundary conditions are also identical. If that happens, when the governing equations are the same, the boundary conditions are the same, then the systems are dynamically similar, and under that condition, any relation that you have obtained, for example heat transfer, can be modified to be the relation for mass transfer, provided you change the similarity parameters corresponding to heat transfer, to mass transfer, and so on. So any relation of Nusselt number which contains Reynolds and Prandtl number can be used because of similarity as a relation for mass transfer, provided you change the Nusselt number to Schmidt number, Reynolds number will remain unchanged, the Prandtl number can be changed to Schmidt number. So this similarity, which is known as Reynolds analogy, which is the most restrictive form of analogy because it demands that Prandtl number and Schmidt number should be equal to 1, the applicability of this analogy can be extended further, which we have seen by incorporating Prandtl number and Schmidt number correction factors, which gave us the modified Reynolds analogy or the Chilton-Colburn analogy. So this is the point which I tried to convey in this course, that everything is similar, all these transport processes are similar if you look at them through the lens of analogy. So all these processes are therefore similar, therefore an unified treatment of heat, mass and momentum transfer is possible. and the last 2 weeks, week 11 and 12, where we are discussing about analogy, this is entirely from the book of Incropera and DeWitt, Heat and Mass Transfer by Incropera and DeWitt, and I have solved a large number of problems on the analogy to clarify the concepts in this. And towards the end, I have also included some problems, solution of some problems which deal with momentum integral equation, because I thought that I should spend more time on that momentum integral equation part. So, overall I have given you a brief overview of the course material, how we have attempted it, a summary of what we have done in this course, and the books which you should follow specific to each of these chapters. So, I think you have enjoyed, I hope you have enjoyed this course, and this is a difficult course because it is very fundamental in nature. So, you have to think, you always have to think and find out how to view, how to express, how to model a system, but at the fundamental level all are similar: mass, momentum and heat. So, that is the take home message that I would like you to take with you, and I wish you the best. Thank you.